Thank you all very much. My name is Joshua Craver. I am a graduate student working at Purdue University with Dr. Roberto Lopez. And so today I'm going to be talking about some research that we have recently been conducting over the last year, where we've been looking at comparing plant responses under supplemental lighting from HPS lamps and LEDs. So I'd like to start out just by talking about traditional greenhouse lighting. And so traditionally, when we talk about supplemental lighting, much like what Dr. Lopez was mentioning, we typically think of high-intensity discharge lamps, or HID lamps. And the most common are going to be the high-pressure sodium, or HPS, and the metal halide. And so obviously with these are going to come some pros and cons. So specifically, when we think about some cons of some of these older HID lamps, we typically think of them being as less energy intensive and potentially having a shorter lifespan, as we've had some new technologies come out recently. Additionally, when we look at HPS lamps, we talked a little bit previously about the radiant heat that they can emit. And so this can both be a pro and a con depending on the grower's situation. So it can be a pro in that you are getting that additional heat provided. While it's not the most energy efficient way of providing heat, many growers do enjoy having that extra heat emitted during the winter months when you're often needing the supplemental lighting and it's very cold outside. However, for some applications, this can be viewed as a con, specifically when you're having to place these lights very close to the plant canopy. Often that radiant heat can cause burning of the plant and actually be very detrimental. Now, in terms of some of the pros, obviously we know that the HID lamps are going to be a little more cost efficient. It's going to be a lower investment cost to have these installed in the greenhouse when we compare them to some of the newer technologies. And also, I think it's important to note that some of the newer HID lamps that are coming out are much more energy efficient. We actually are finding some increases in this energy efficiency as we've had some developments with electronic ballasts as well as double-ended fixtures, which I believe will be discussed later on in this webinar. And so that really leads to this new technology that I was alluding to, which I'm sure we're all pretty familiar with, being light-emitting diodes, or LEDs. And really, a lot of research has been looking recently at how we can use these LEDs as potentially an alternative lighting source for many greenhouse applications. And the reason why these LEDs are becoming a pretty hot topic and becoming more popular is because they are generally thought of as being more energy efficient. And so ultimately, a lot of growers are seeing that potentially you can save a lot on energy costs when you look at installing this type of lighting in your greenhouse. Additionally, with the LEDs, we do have the ability to select specific wavelengths of light. And so this can be beneficial, as specific wavelengths of light have been found to elicit a specific morphological or physiological response in the plant. And so with these LEDs, we do have the capability to try to manipulate a crop to do specific responses that we may want. Additionally, with LEDs, typically you're going to associate them with a generally longer lifespan. And so for the top lights that I'll be talking about in a little bit, generally that lifespan is thought to be around 25,000 hours. However, there are some cons that come with this LED technology. Specifically right now in the current market, it is a very high investment for most of these modules to have them installed in a commercial greenhouse. And additionally, like I alluded to on the previous slide, these LEDs are going to have a lower output of radiant heat. And so for some applications, like if you look in the bottom right corner of your screen, you'll see this is an application known as sole source lighting, where we're growing these crops solely under LED lighting. There's no solar ambient light. And so with this type of application, we have those LEDs mounted very close to the crop canopy. And so because of this low output of radiant heat, we're able to use this application, whereas if we were using something like an HPS lamp, we would have some issues in terms of burning, and it would be of consequence to the crop. So the main focus in terms of LEDs today is going to be for supplemental lighting, obviously, and what we'll be looking at is LED top lighting. So this is a new technology that's recently been released by Philips. And really the main draw to this is that it has a comparable distribution and intensity to HPS lamps. And so generally when we think of many LED applications in the greenhouse, we think of a high density of these LED modules that's going to be necessary to get an intensity high enough to grow a crop efficiently. What these LED top lightings are trying to do is to reduce the density of modules that are needed to adequately provide supplemental light to a crop. So really trying to provide an alternative potentially to HPS lighting. Now, in terms of the research that I'm going to be talking about today, the main focus is going to be on plug production, which, as the previous presentation alluded to, plug production is one of those areas where we find a lot of benefit from providing supplemental lighting. And so specifically, one of the areas that we want to focus on the most is the quality of the plug that we're producing under these different supplemental lighting sources. And so when I'm talking about a quality plug, generally some of those attributes that we're wanting to look at is how compact is that plug. We're also looking at the stem caliper. So generally it's thought that a larger stem caliper is going to be better. Also, we're looking for higher amounts of dry mass, both in vegetative as well as root dry mass. And then we're also looking at leaf area, where we want a smaller leaf area to try to prevent shading, and also, again, to keep those plugs nice and compact. And so ultimately, when we look at all of these attributes together, what we're looking for is the highest quality plug possible that's going to make shipping easier. You're going to have less breakage in shipping, damage in shipping, as well as in transplant. And then we're also going to have a plug that's hopefully going to be established and finishing much more quickly when it is transplanted. Now, in addition to the plug quality, we're obviously also concerned with timing. And so looking at how supplemental lighting can potentially help us to increase the turns in a greenhouse and get these plugs shipped out more quickly. And so this leads to the research that we were recently conducting at Purdue University, where we were comparing HPS lamps with LED top lighting. And so specifically, this was research that was not done on the Purdue campus. We actually worked with a local greenhouse known as Gallima's Greenhouse, where we were able to establish our lighting treatments and actually conduct this experiment. So it is very much a trial that occurred in a commercial greenhouse. Two main areas that we were wanting to look at was obviously the plug production, but we didn't want to just limit ourselves to looking at how these light sources affected plugs. We also wanted to look at that finishing component to see how this light may be beneficial or used in finishing production as well. And so here's an example of the way that we set up these experiments and the light sources that we used. And so in the top left, you'll see we have 600-watt HPS lamps that were provided by PL Light Systems. And then in the bottom right, we have our 200-watt LED top lights, which were provided by Philips. And so you can see the differences between those two treatments there. Now, in terms of our propagation environment, we sowed these seeds in 128-cell plug trays. And the air temperature set point in the greenhouse where we were growing these crops was 77 degrees Fahrenheit. Now, what we really want to be looking at, obviously, is the propagation DLI. And so if you look starting at the top left, you'll see we have our HPS treatment. And we have a target set point of supplemental light set at 70 micromoles per meter squared per second. And so this was what we established for that HPS treatment to be supplying to the plant in addition to the ambient light that it was receiving. And so ultimately, when you look at the average DLI that we were getting in that treatment from February to March, our average DLI was 10.9 moles per meter squared per day, which, if you'll remember from the previous presentation, that target of 10 to 12 moles per meter squared per day is really what we're aiming for to produce a high-quality floriculture crop. So we found that we actually hit that right on the nose, right in the middle of that 10 to 12 target. Now, if you look at our LED treatment, you'll see that our set point was exactly the same. We were targeting a set point of 70 micromoles per meter squared per second of additional light provided to these plants over a 16-hour photo period. And overall, our average DLI in this treatment was 11.9 moles per meter squared per day. So again, we were right in the middle of that 10 to 12 target. Now, in addition to the two supplemental lighting treatments, we also wanted to evaluate how the plugs would be produced if we didn't grow them with any supplemental light, also known as our ambient or control treatment. And what you'll see is that in this treatment, we had a significantly lower DLI of only 5.3 moles per meter squared per day. And so you can see there's a fairly big difference between our supplemental lighting treatments and our control treatment. Now, in terms of the propagation data we collected many different measurements trying to look at the quality of these plugs that we produced. And unfortunately, I'm not going to have time to go through every single one of those measurements today. But the one measurement that I would like to focus on is known as the quality index. And the quality index is an objective, integrative, and quantitative measurement of quality. And so what this is it is a tool that allows us to integrate morphological parameters that contribute to a high-quality seedling. So what we're able to do is take many of these quality attributes that we're collecting data on and combine them into one number known as the quality index. And so what you'll see is if you look next to a quality index there at the top, you'll see that we have an equation, and I'll quickly walk us through this equation. So the first acronym is TDM, which stands for total dry mass. And so we're looking at how much biomass was this plug putting on over the course of the production cycle. Now the RS is going to stand for the root to chute ratio, and so looking at the ratio of the root dry mass to the chute dry mass. And then the last acronym is SQ, which stands for sturdiness quotient. And what this is it is taking the caliper of the seedling, the stem of the seedling, and dividing that by the length of that stem. And so ultimately what we're looking at is how sturdy is this seedling. With a larger caliper and a shorter length, ultimately we're going to have a higher value for this SQ, which we're going to correlate then to a sturdier seedling that's not going to be as easily broken or damaged in shipping. And so when we take all these components into account, ultimately that number that we get as a result, we would call the quality index. Now, in terms of this study, we looked at many different species, specifically 7 different common bedding plant species. But again, due to time restraints today, I'm only going to be able to cover a few. And so we'll be specifically looking at New Guinea Impatiens, French Marigold, Petunia, and Zinnia. So starting with the Impatiens, if you look at the top of your screen, you'll see that I do have the equation for quality index still listed up there at the top. And then under lighting treatments, we have our 3 light treatments of our HPS, LED, and control, which was receiving no supplemental light. And then if you look at the bottom of each seedling, you'll see that value, which is the value of the quality index. And this was seedling data collected at 21 days. And so ultimately what we found is that the HPS and LED supplemental lighting treatments performed very similarly. Both of these treatments gave us very high quality index numbers. But when we compare that to our control, you see that we have significantly lower values. The control did not perform as well as when we were providing that supplemental light. Now, very similar results were found for Marigold in that we had similar values between our HPS and LED treatments, but then we had a huge gap as we began to look at our ambient or control treatment, where we only had a quality index value of 4.6. So you can see overall we had much lower vegetative tissue, root tissue, and the caliper and the length was also not in a good combination for that high sturdiness quotient. Additionally, for Petunia, very similar results where we had higher values under our HPS and LED treatments compared to our control. And much like you've been seeing in the past few slides, the LED treatment was performing slightly better. So specifically with this Petunia seedling, you can see it's slightly more compact, but ultimately these values are very similar to one another, and we got very high quality seedlings under both supplemental lighting sources. Now lastly, looking at the Zinnia, again, it's the exact same story, where you'll see that with our HPS and our LED treatments, we had very similar values, and then with our control treatment, we had a fairly large drop in value in terms of the quality index. Now, we didn't want to just focus on the plug production, we also wanted to look at our finishing environment as well. And so in this finishing environment, we had a greenhouse air temperature set point of 18 degrees and 15 degrees Celsius day-night, and we transplanted these seedlings into 4.5-inch pots. Now, in terms of our lighting treatments, we had the exact same treatments that we tried to establish for our propagation experiment. So we had supplemental lighting from our top lighting and our HPS providing 70 micromoles, and then we had our no supplemental light treatment or our control. And so you can see that our average DLIs were very similar to what we received in our propagation experiment. All right, so this is just an example of one of the pictures and some of the data that we collected on this finishing stage of the progress. Of the study. Unfortunately, I'm not going to be able to share a lot of the data because I am limited by time, but what you'll see on the top is that we have our propagation lighting, which is HPS, LED, and ambient. And so what we tried to do was transplant plugs from each of our propagation lighting treatments into each of our finishing lighting treatments. So for example, we wanted to transplant plugs from our LED top lighting propagation treatment into potentially our HPS finishing treatment to see if there was any carryover or any interesting interactions between those. And so that's why you'll see each of the propagation lighting treatments represented in each of these finishing lighting treatments. And so ultimately what we found was that the HPS and LED finishing treatments performed very similarly. We did have slightly earlier flowering for some of the HPS treatments, specifically for Zinnia like you see here, but ultimately they performed very similarly. And when we compare them to ambient control, you can see that again we had that increase in biomass when we compare our control treatment to the lights. So how much initially is it going to cost to put the HPS lamps in a greenhouse versus the LED top lights? Additionally, looking at energy efficiency. So is it more energy efficient to install the LEDs, or maybe there are more energy efficient HPS alternatives? Also, an important thing to look at is going to be the radiant heat output. Obviously, you're going to get that additional heat from the HPS lamps, and whether that's a consideration that you want to include is also important. And also in terms of lighting spectrum. And so what you'll see in this picture on the right is that we have the top lighting, and we're providing solely red and blue wavelengths of light. And so what we actually ran into is some of the employees at Gallima's greenhouse started to complain as they were working on these lighting sources that they were maybe getting a headache or that their eyes were hurting. And so this became an issue, and it became a concern, and it's one that has actually been addressed to an extent, and I'll talk about that a little bit in our next slide. But ultimately, some other things that you obviously want to consider are, can you use these lights year-round? Are there any rebates in terms of which lighting source you decide to choose? And then ultimately, looking at supplemental lighting as a whole, if I install these supplemental lights, can I increase my turns? Can I increase my yields? And ultimately, is this going to increase profits for the greenhouse? Now, going back to that lighting spectrum issue, one of the ways that this has been addressed is known as white LEDs. And these aren't necessarily white lights supplied to the plants. What it actually is green wavelengths of light that are added into the ratio. So to better explain this, if you look at the picture on the left, you'll see that we have red, green, and blue LEDs. And what you'll notice is that this gives off the perception of white light. It's much easier to see when a plant's drying down. You can more easily see if there's disease or pest issues. And it's also much easier on the eyes for those that may be working in these environments. And so when you look at the picture on the right and compare those red-blue treatments to that red-green-blue treatment, you can really start to see the difference. And so, this is becoming a increasingly popular alternative to try to help alleviate some of those issues. So I would like to go ahead and acknowledge first and foremost Gallima's greenhouse for providing the greenhouse space for us to be able to conduct this experiment. Also the USDA and SCRI for Lopez Lab and greenhouse staff for helping me to conduct this experiment. I'd also like to thank Philips Lighting for the top lights, as well as PL Light Systems for the HPS lamps, and for also putting on this webinar. And also I'd like to thank Ball Horticulture Company for providing the seed for this experiment. And so with that, I would be happy to answer any questions that you might have with the remaining time that I have left.